Hello everybody. Hello everybody. Myself Dhiren Chetrupal, and today we are going to discuss one of the topic from the chapter Chemical Kinetics. The topic is zero order kinetics. Before starting this topic, I believe that you all know what the means of kinetics. Actually, my dear, the kinetic words derive from the term kinesis, which means movement. Uh, Now we are going to start zero order kinetics. First of all, what is actually zero order kinetics? So, any reaction in which the rate of reaction is independent of the concentration of the reactants that are involved in the reaction, such reactions are known as zero order kinetics. Let me write down, that is any reaction in which the rate of reaction is independent of the initial concentration of reactants involved in the reaction. What I mean to say, what I want to say actually, let's suppose we have a reaction having the reactant A and it is converted to the product P with the rate constant sum K. Now, my dear, we can write this reaction as a rate can be written as minus dA by dt. My dear, I hope you know what's the meaning of minus over here. This minus actually represents that there's a decrease in concentration of reactant over the time. Okay. And this rate can also be written as K A having time t to the power 0. Now, what is actually the 0? This actually the 0 represents the zero order of the kinetics. As we know that order cannot be predicting by observing the reaction, it is always experimentally measured. Okay, so we can say from the experiment it is like k a to the power 0 or k. One more important thing is this whole expression is actually the differential rate law. This is actually the differential rate law. Now, what the actually zero order says, as we know, my dear, that for any reaction, the rate of a reaction is directly proportional to the concentration raised to the power order. And if we remove the proportionality constant, we need to write the rate constant K with the some concentration having the order this. And we are saying that the reaction is zero order kinetics. So if we put the order to be 0, then a rate is nothing. It will be what? The K. This is actually the definition of zero order kinetics. That is, the rate of reaction is independent on the concentration of the reactants involved in the reactions. Now, again, maybe the question arises, sir, what if there will be more than one reactants? So let's suppose we have more than one reactants, and again the reaction follow the zero order kinetics. Again the reaction follow zero order kinetics. So we can write that rate is equal to minus K dA or minus dA by dt for the reactant A, or it can be equal to minus dB by dt for the B as per the rate law definition. And this can equal to be K A to the power 0 and B to the power 0. Sir, so we can also be write, there's so many way to write this expression. We can also write A to the power 1 and B to the power minus 1. Okay, sir. So we can also be write a to the power plus 2 and b to the power minus 2. These all are the actual expression of zero order. Zero order. Sir, actually then what the meaning of zero order is? Again, the zero order says the rate of the reaction is independent of the concentration of the reactants. That means the overall reaction should be zero order if someone says the reaction is zero order. However, the reactant must have their own initial concentrations. You can see this, plus 2 and minus 2 is also 0, plus 1 and minus 1 also 0, and there are n patterns we can draw for the zero order. So my dear, actually the zero order means those reactions in which the overall the concentration, that is the sum of the power of the concentration should be 0, which is expressed in the rate law expression. However, the reactants have their own concentrations. Okay, this is actual the meaning of zero order. Now, for example, there are actually some few examples that are observed in the chemistry for the zero order. Some reactions, that is chemical decomposition, gaseous decomposition in metal surface follow zero order kinetics. Right? For example, let's say is ammonia on decomposition just changes to N2 or H2. So this decomposition will take place in the surface of the platinum metal at high pressure with the temperature some T. This actually follow the zero order kinetics. In the same manner, we have the reaction again 2Hi in the surface of gold. Gold is metal. Okay, at the high pressure P, this is breakdown into H2 and I2. This is also zero order kinetics. Again, remember, order is always experimentally measured. This cannot be predicted by seeing the reaction. You can't say, sir, here is a 2, and then you can say that order is second. No. The reaction is actually the zero order. This is completely experimental data based. I hope you are getting my point. So this is what the zero order is. Now, in the zero order, we are going to start one of the topic known as integrated rate constant for zero order. So before starting this, first of all, we want to know why we need to calculate the integrated rate constant. Actually, dear, integrated rate constant is thus nothing. It is just a mathematical expression of differential law. This actually helps us to predict how much the amount of the reactant is reacted and how much the amount of reactant is left. If one wishes to calculate how much the amount of product is formed, this can also be calculated by the help of this integrated rate constant. One more thing, this integrated rate constant is calculated for all the type of order of the reaction. Currently, we are discussing for the zero order. The main basic motive to calculate the rate constant is to identify how much the amount of reactant is react or how much amount of reactant is left. Okay, I hope you are getting my point. Let me calculate the integrated rate constant. Let's suppose, my dear, again we have a reaction having reactant A and changes to product P. Now, most important, we are assuming a simple reaction. Why I am saying the simple reaction? I will take some complex reaction after this simple reaction. If I am saying a reactant is A and changes to product P having the rate constant K. So we can write the reaction as rate is minus dA by dt, which is equal to K A to the power 0 as per the definition of zero order, which is equal to actually the K. Or we can say minus dA is equal to K dt, right? Now, if we integrate both sides, integrate both sides, we get what we get, my dear? We get minus dA of integration is min or k integration of dt. We need to integrate this. So in general, what we know, that the integration of dx give you x. So that integration of dA gives you a, and the integration of dt is t, having some constant c. This is the mathematical data or the mathematical values with a constant c. Now let's assume at time t is equal to 0, when the reaction is not started yet, at the time the concentration of the reactant is equal to the initial concentration. This data represent the initial concentration. Okay. Now if we will put this value over here by using the time t, we actually get the C, that is minus a naught k into 0 plus C. From this gives the intercept for the graph, that is C. And by putting the value of C in this equation, this gives us minus a is kt minus a naught. From here we get the value of k, and this k is nothing, it is a naught minus a over t. This is actually the value of rate constant for zero order kinetics. Remember, my dear, this value may change if the stoichiometry of the reaction will change. I will explain in later. Before, first of all, what is actually a naught over here? What is a naught over here? What is a naught? A naught is nothing. A naught is the initial concentration of a reactant at time t is equal to 0. Most important is actually this A. This A. What is actually this A is? What is A over here? My dear, this A is the amount of reactant left. This is one of the most important point. Amount of the reactant left. How much amount the reactant is left is represented by this, the term value A. For example, if I am saying, let's suppose the initial concentration of reaction is 10 moles per liter, and the concentration is left after let's suppose 10 minutes, let's suppose hypothetical 10 minutes, it will be 6 moles per minute, per moles per liter, sorry. So the value of rate constant is 10 minus 6 by 10. This is, the value is 4 by 10, or you can say the 0.4 mole liter inverse minute inverse. This is the unit of the zero order kinetics. Now what is actually the 0.4 says? Just again recall the definition that zero order is independent of the concentration of reactant, right? So rate constant is actually 0.4, means the rate of reaction will consumed with every time period will be 0.4, because zero order kinetic actually says that equal amount of reactant will be consumed in an equal period of time. That's why, because this is always the constant. If the time remains constant for the next 10 seconds, 10 minutes, again the value will be same. The amount of the reactant consumed will be same. This is actually the definition of zero order. I hope you will understand this value. If you again put this value 0.4 and you need to calculate the how much amount is left, this will be the same, or the amount of product will be same. This is actually the, you can say, the characteristic or zero order, the beauty of zero order is. Okay. So this is need to learn that the rate constant is a naught minus a by t. Okay. So this is actually the integrated rate constant for zero order kinetics. I hope you are getting my points. Now, next, we need to calculate the half-life for zero order. Zero order. First of all, before explaining the zero order half-life, what is actually the half-life is? The most important question is, what is the half-life? My dear, half-life is nothing that it says that how much amount of the reactant will react in the half period of time, or how much the amount reactant left, or you can say the amount of reactant, half of the amount of reactant is left in the period of time. What I mean to say, let's suppose, my dear, if the initial concentration is A naught, if the initial concentration is A naught at the time t is equal to 0, and if I am saying when the reaction is consumed at half time, at the time the concentration amount A is left is nothing, it's the half of the initial value. That means if someone says the half-life, that means half of the reactant is consumed or it is converted into product by this expression. So the amount left that we have is A naught minus A naught by 2 is nothing, it is half of the initial amount. This is actual the definition of half-life. Okay, now we can put this value in the formula of rate constant, that is K is A naught minus A by T. Okay, now if we'll put the T changes to T half, representation for the T half, this will be A naught minus, now what is A over here? A is the amount left, that is half of the initial as per the definition of half-life, upon K. And this T half is, my dear, this A naught by 2K. This is the final expression for this half-life of zero order. That is T half should be equal to A naught by 2K. Okay. And one more important thing is, we can also conclude that the T half is directly proportional to the amount of initial concentration. Okay, that means more the initial concentration, more will be the half-life. This is again, you can say, the second characteristic of zero order. Okay. Okay, now sir, can we calculate the 3/4 life or something x by y life? Yes, we can calculate any life. That is, let's suppose we need to calculate the T 3/4 life, or this can also be represented as T 75%. Now what's this meaning is this? When someone says T 75%, it means 75% of the reactant is converted into product. Or you can say T 3/4 amount is reactant is converted into product, or 25% of the reactant is left. This is very simple. That means let initial concentration to be A naught, then the A will be, my dear, A will be initial minus 3/4 of the initial. That means 3/4 of the amount is consumed. That's why we are using minus over here. Okay, so what we receive, what the left is A naught by 4. This is the amount of the reactant left is the 1/4 of the initial, or you can say 25% of the initial. Okay, now this can also be put in this value, of, that is K is A naught minus A by T. So if we put the value T 3/4, this will give you, my dear, A naught minus, put the A over here, this will give you A naught by 4 upon K. And on solving this 3/4 is 4 minus 3, that is again 3/4 A naught of K. So we can also calculate the T 3/4. Even you can calculate x by y, but the most important, x should be less than y. You can calculate. Okay. So sir, now the next question which is come in the mind, sir, okay, fine, we can calculate the T 50%, we can calculate the T 75%. Sir, then what is the meaning of T 100%? What is the meaning of this? T 100%. It means 100% of the reactant is converted into product. Sir, is it possible? Then my answer is, my dear, for the zero reactions, this is possible, that in case of zero order, 100 we are assume that the 100% of the reaction is converted into product. Then how much the reactant is left? Nothing will be left, my dear. It is 100 converted to product, and this is also known as lifetime. Lifetime. Okay, that means 100% of the reactant is consumed, that is A naught minus A by T. Now nothing is left, this should be 0, and this converted to be T 100%, and this T 100% is A naught by K. Okay. Then we can also say that, sir, T 50% for the zero order, sir, is A naught by 2K, and sir, T 100% is this. So, sir, can we calculate can we relate the relation between this? Yes, why not? We can say that the T 100% is twice the T 50%. Okay, twice the 50%. But again, my dear, this is only valid for the zero order kinetics, because first order or the rest of the order we are assuming it is not complete over the period of time. Okay, even the NCERT says the first order reaction will never goes for completion. Okay, so this is the 100% order, or this is the half life, and this is 3/4 life. Okay, fine. I hope you will understand. We will go for the question after some time. Now again come to the back point where I have written that the whole data is actually for the simple reaction. So then what do you mean by the term complex reaction? Okay, fine. What do you mean by the term complex reaction? Complex reaction means nothing. When I am saying, when the case, you can take the case when the stoichiometry of reactant is, let's suppose, to be A. Sir, before this I have taken the stoichiometry of reactant to be 1. The whole expression or the whole derivation is derived and to be assumed that the initial stoichiometry of the reactant to be 1. Now I am saying, let's suppose if the stoichio of the reactant is changed, then the question is, sir, is the half life or the rate constant value will change? Answer is yes, no doubt it will change. Let's say just I am taking an example. Let's say now we have 3A and changes to product B. This is 3A changes to product B. Fine. And in this case, when we need to write the expression, this will be rate is minus 1 by 3 dA by dt, which is equal to K A to the power 0. My dear, now this 1 by 3 will change the integration data. This will change the integration data because before in the previous derivation we have put the 1 by 1. Now it is 1 by 3. Okay, because now 3 will be, it's like minus 1 by A dA by dt is K, or minus dA by dt is 3 of K. Okay, or 3 dt. That means this will, on integration, this will affect the actual rate constant value. So, sir, then what is the general data that we need to learn for the zero order? What is the general data? So, the general data says, let's assume A moles of reactant is A, changes to product P having the rate constant K. Now we can write that rate is minus 1 by A dA by dt. As we know, this is the rate law expression, is equal to K A to the power 0 for the zero order kinetics. And again on the complete derivation, I am not going to go for the derivation, I am just writing or changing the formula. Before the formula was A naught minus A by T. Now my dear, the formula will change. What the change in the formula? This stoichio will become is over here. That means the rate constant will change now. So sir, if the rate constant will change, sir, T half will also change. Yes, why not, my dear? T half will also change. That is, T half is A naught by 2 into K. Now what we will write? We will write A into K. So what I believe and or what I suggest to the students, just you need to learn this data or this data, because you don't know the question comes will one stoichiometry or any stoichiometry. Okay, I hope you will understand this terminology, that what I mean to say, what I want to say, that if there is a change in the stoichiometry, then the rate or the rate constant actually in the T half expression will change. Okay, and I believe that you will understand what I want to say. Now we are going to draw the graph for zero order, graph for zero order. Graph for zero order, there are so many graphs can be drawn for the zero order. First, let's suppose we need to draw the amount of the reactant left versus the time t. So for this, as we know, K is A naught minus A by T. We can manipulate this value in such a manner that the A comes in a y-axis and this T come along the x-axis. So this can be written as K into T is A naught minus A, my dear, or we can write as A is minus KT plus A naught. I hope you can rearrange this value, and please compare this data with the straight line equation, that is y is equal to mx plus c, and on putting the value of data, that A over here slope is minus k, that means slope is negative, time over here slope is negative, so this data changes to this, having the intercept c. This is the intercept c, and this c is nothing, it is what? The A naught. Now how we will read this data? The way to read the data is, when the time is 0, then the concentration of the reactant is equal to the initial concentration, and as the time goes on increasing, the concentration of the reactant decreases. So then what is this point? This is actually the lifetime point, or the T 100%. T 100%. This point where the nothing amount of the reactant is left, or the 100% amount is converted to product P. Okay. So this is the graph for the concentration of A versus time T. Now next graph for the zero order is half-life versus the initial concentration. This is very simple graph. As we know, T half is equal to A naught by 2K. Just you need to put this value in, y is equal to mx. Okay, this is very simple data. That is T half along the y-axis and x should be along the x-axis with the value of A naught as per the question, and the slope is 1 by 2k. Okay, the slope is positive with the zero intercept, right? So we can start this graph from this way, and we can write the value of slope. It should be 1 by 2k. Okay. Okay. Now third graph is important. We need to calculate the amount of product versus time. How much the amount of product is consumed after the time t, and we need to draw the graph for such experiment. Before this, first of all we need to calculate how much the amount of reactant is converted into product, or to calculate the amount of product. That is, let's suppose we have a reaction A changes to product P having the rate constant K. Let's suppose at the time t is equal to 0, the initial concentration is A, and that the time t is equal to T, let's suppose X amount is converted into the product P, then the amount left is A minus X. Just nothing, we need to put this value. As we know, K is A naught minus A by T. So on putting this value, A naught is again, my dear, is an initial concentration, that is A, minus what is A? The amount of the reactant left, that is what? A minus X upon the time T, and by this value this will be A minus A plus X by T. And this is what the X is, the amount of the product obtained at a time T having the sum rate constant K. Okay, now we can draw the graph, my dear. As we know, X is K into T. Thus relate this graph is again Y is equal to mx. Again this graph says along the x-axis, X is what? Amount of product versus the time T. Again this graph is straight line. This also shows the amount of product will form as the time increases. It's very obvious. Okay, so this is the amount of product that is obtained after the time T. So these are some common informations about the zero order. Remember, one of the more important thing, zero order characters are very important for this, and I hope you will understand this lecture. Now we are going for some questions that we that was asked in previous PYQ NEET. Okay, so let me take some questions of the NEET PYQ from the zero order kinetics. From the zero order kinetics, I have some questions. Okay, let's suppose now this question was asked in NEET 2020. Okay, the question says the half-life for zero order having 0.02 molarity initial concentration. This is the given for the initial concentration of a reactant is 100 second. Calculate rate constant. Okay, this question was asked in NEET 2020. This is a PYQ question. First of all, while solving the question, what are the important data that we need to remember to solve the question? As per the given data, the reaction is zero order, having the initial concentration of 0.02 molarity with the half-life of 100 seconds. These 3 points are given to us, and question says calculate the rate constant. First of all, write down the data, what the question given. We have the initial concentration, that is 0.02 molarity. We have the T half, that is 100 second, and we need to calculate the K. This is very simple. In general, if the question is not explained or not given that what is the stoichiometry, remember we need to assume the stoichiometry should be 1. This is most important, because as we know, if we change the stoichiometry, the overall data will be changed. So nothing is mentioned over here. So just we need to put in the formula that, as we know, T half is A naught by 2K, and we need to calculate the K. So K is A naught by 2 into T half, right? Now what is this A naught, my dear? As per question, it is 0.02 upon 2, and the half-life is, I think it's 100. And solving this equation, this 2 can be cancelled, and this will give you 10 to the power minus 4 with the unit of mole liter inverse. Data is in second, so it will be second inverse. Unit is very important, and I hope you know how to calculate the unit for any order. Okay, So this was a question was asked in NEET 2020. Coming for the next question. Next question we have. This question was asked in NEET to 2015. Okay. Question says a reaction A changes to B having the rate constant is 6 into 10 the power minus 4 moles per liter per second. Question is, if the concentration of A is 5 m, then concentration of B after 20 minutes. This is the question. Concentration of B after 20 minutes. Okay. Just wait. Okay. Again, just be calm for the question. We have the rate constant value. Fine. And the question given as the concentration of A. My dear, before this, we need to know this is actually the zero order. How I can identify this is zero order? By the unit of this value. Okay, in higher or in the next lecture you will learn the value of rate constant, or I hope you will know. So this is nothing, we do nothing with this. Why? Because zero order reaction is independent of the concentration of the reactants. And the question says calculate the amount of product, that is B. We need to calculate the amount of product. So amount of product, as we know, is nothing, it is K into time T. This is the simple. And we know the value of K, that is 6 into 10 the power minus 4. Multiply with the time. Remember one thing, time is given in a minute and the rate constant unit is in a second. So you need to convert this minute into second, and as we know, we can multiply with 60. So I think 6 2s are 12 and 12